Hi, my name is Gracie, and this is my presentation for Physics 2 Lab 5. The purpose of this lab is to understand the properties of Faraday's law using a bar magnet dropped through a tube of aluminum foil. The most important fundamental concept in this lab will be Faraday's law, with other concepts including the magnetic field of a bar magnet as well as gravitational force. A brief overview of results. In the experiment, the average time it took for a magnet to pass through a cylindrical tube of aluminum wrapped around a paper towel roll was about 1.34 seconds. Meanwhile, in the computational model, it predicted that the magnet would pass through in about 3.02 seconds, making a strong difference between the two results, which we will discuss later. The experiment design was quite simple. The system was a bar magnet, and the relevant surroundings were the aluminum foil tube and the Earth's gravitational pull. Initial conditions were holding a bar magnet north side pointing down above a tube of aluminum foil. Record the amount of time it takes for the magnet to pass through the tube and repeat 5 times. A very interesting effect was observed where the magnet seemingly slowed in the middle of the tube, stagnating there before falling out of the bottom. This is due to the induced magnetic field created as the magnet moves through the tube, resulting in a change in flux that nature is attempting to counteract. The results of our experiment are shown here in this figure, and the average time of the magnet moving through the tube being 1.341 seconds. For the computational model, I started with the starter glow script code given in the Lab 5 page. The most important aspects to note are the dimensions of the tube and the magnet, the creation of the B field from the magnet, the corresponding flux as it moves through, and then finally, this is important for Faraday's law, the induced counteracting forces created by nature against the change in flux. The coding produced a time velocity graph as well as a model of the magnet as it moves through the tube. As you can see, velocity will stagnate as it moves through the tube before it restores its speed on its way out, similar to our experimental model. The stagnation in velocity of the magnet as it goes through the tube is due to the induced EMF produced as the magnet moves through, causing a change in flux. This induced field temporarily impedes the force of gravity on the magnet, causing its fall to slow down. Generally speaking, the computational model produced very similar results to our experiment in terms of the movement of the magnet. However, the time predicted and observed differed quite a bit, by 76%. There are a few factors that can explain this, including the fact that the computational model assumed the movement of the bar magnet started right at the point of entry, whereas we dropped our magnet about 2 to 3 inches above the tube's entry. Furthermore, a tube of aluminum foil is an imperfect and inconsistent conductor that is likely not as consistent throughout like a computational model would be. Another potential source of error is that this is an open lab, meaning the materials have likely been used before that can further alter the predicted results. What if the resistivity of the conductor were reduced as close as possible to 0? A lower resistivity, meaning a higher conductivity, would lead to a much stronger induced EMF, making the velocity of the magnet fall very low, potentially close to 0. What if holes or slots were cut into the tube? Without consistent rings to conduct an EMF, the induced B field would be impaired. In the model, the ring currents would be weaker. Thank you.